We welcome you to ASHRAE Tech Hour. Our subject today is commissioning. We welcome Jay Enck, co-founder and chief technical officer of commissioning at Green Building Solutions, Inc. Jay is a mechanical engineer credited for the creation of the holistic commissioning process. He's a well-established innovative leader in commissioning, operational efficiencies, building enclosure forensics, green design, and sustainable development. With over 40 years of experience in engineering, construction, building operations, and whole building commissioning in multiple market sectors. We also welcome Reinhard Seidel, principal at Taylor Engineering LLP in Alameda, California. Reinhard is a registered mechanical engineer with an MS in mechanical engineering from the Delft University of Technology in the Netherlands. He has over 25 years of experience in the construction and commissioning sector, both as a project engineer and project manager for a design-build contractor and as a consulting engineer. Reinhard has focused on commissioning projects for the last 10 years and worked extensively with PG&E and other industry partners to help develop and bring a free trend analysis tool to the engineering community, along with training classes for its use.
Welcome to this ASHRAE Hour on existing building commissioning. We're going to talk today about a number of learning objectives for this class, and existing building commissioning isn't a new topic. So we're going to talk about why it is especially important these days. And we're going to illustrate that with three main learning objectives. One is we're going to talk about why it is especially important now to commission our existing building stock. Not that that's an entirely new science, but we're going to talk about what it is that changes it in this day and age. Then we're going to talk about if it is important, then how are we going to do it? So we're going to talk about the correct steps to undertake, largely focused on controls. And then we're going to talk about what the new technologies are. In many cases, those are very recent and only a couple of years old, that can help us improve the process by which we do building commissioning. So one of the main drivers for making building commissioning more important than in the past is climate change. I am a resident of California, and to me, climate change is now a not daily occurrence, but certainly a very clear annual occurrence. The wildfires here have now become almost continuous throughout the year. And we had employees in our office whose houses burnt down or whose parents' houses burnt down. That really brings it home. These aren't far away in the future events. They're real and they're happening now. So that changes the paradigm for the reason for commissioning somewhat, because in many cases, as commissioning started 10, 15 years ago, the main thrust of it, or the main purpose, was to reduce the energy bills for building owners. That's still the case, obviously, but it isn't enough of a driver. The larger driver should be that we're trying to prevent the worsening societal impacts that are occurring because of climate change. And of course, energy use is one of the key drivers of that. So we have the potential of reducing some of the impacts, which are now becoming impacts to all of us, rather than the building owner who has to foot the utility bill for a building. So the effects of things like wildfires in California easily run into the billions of dollars, not just for extra services for firefighters that have to be paid, but also impact the people's lives, homes lost. And of course, California wildfires are close to my mind, being a California resident, but there are also effects such as sea level rise, flooding, which have been predicted for many years and which I think have not yet fully hit home, but which will do so in the coming years. And as a result, the effect or the importance of having an effect on energy usage matters much more so than in the past, I think. And in addition, I think those ongoing effects that we're seeing now on a daily basis by just reading the news are going to accelerate and get worse as we have certain tipping points, such as the continued deforestation, which in itself can lead to not just trees that have been cut down being turned into carbon, but also a reduction in the carbon that's absorbed because those trees are no longer regrowing. And of course, recently in the news, changes in oceanic flows that will change temperatures. So there are many large effects that affect every single taxpayer.
From what you've said, Reinhard, certainly you've iterated what is often what we see in all the climate forecasts. Every single year, we are emitting more greenhouse gases than the previous year. We have to be asking ourselves, what are we going to do to change energy in all sectors, including the forms of energy use in transportation, electrical generation, agricultural, residential, and commercial buildings, and industrial use. The price of failure, as you've been pointing out, is just showing up and dwarfs what our current pandemic has cost us in financial as well as loss of life. And it will not be something that can be fixed in just a couple of years.
So there is a paradigm in the way that we have done business in most Western countries for the longest time, which is that we pay essentially for goods and services only for a small portion of what the actual effect is on climate or the world overall, which means we, for example, don't pay for the cost of garbage disposal or for the cost of decontaminating properties on which buildings were built. And the same is true for energy. We don't really pay for the effects of energy consumption. We just pay for the extraction and transportation of energy. And so the overall cost picture is really skewed, and it seems like that bill is coming due shortly. And efforts like carbon credits to shift that balance somewhat and to include the cost of not just production, but also cleanup in the price of utilities, I don't think is happening fast enough. So it puts more of a burden on us to just also reduce energy use rather than find a fairer way of paying for it.
So I'd like to add here to, the cost of survival for millions of people that are living along the equator, which will be impacted as we have a rise in global temperature as a result of climate change, is certainly going to cost mass migration to occur just to be able to survive, not just thrive. Changing how we use energy along with the transition to a carbon-free energy is essential to avoid disaster and climate change, which will be showered upon us as a people and as a planet. Here's an example of an institutional commercial building. It's on a university campus in Atlanta, Georgia. Completed in 1997. It's 123,000 square feet. It was selected because it was one of the best buildings on campus to go through the LEED for existing buildings process. It had only had 13 work orders, and they were not significant in nature, and there were no current occupant complaints. They were monitoring energy usage, but they were really not analyzing how the energy was being consumed. It was considered one of the best buildings on campus. Energy Star is a great tool to use to be able to understand how your building is performing compared to others. In this case, for this building, it scored 58, which is better than half the buildings in the United States. But its performance is not as best as it could be. As you can see, there's a steady increase in energy consumption. There were a number of factors that we identified during the process where we had a change in schedule because a professor came in at 3 o'clock in the morning and complained to operations and maintenance that he was uncomfortable. So they changed over the building to 24/7 operation. They also had problems with the mechanical systems as far as crossover points and controls, which allowed simultaneous heating and cooling and reheating and cooling in the VAV systems. They also had restrictions in the pressure intakes, and we're running higher than necessary static pressures in the air handling units. So that created over time, because the degradation in performance of the building, a steady increase in energy consumption. You can see that having 400,000 pounds of steam consumed in August in Atlanta, Georgia, which has very warm outside temperatures. That's a certain clue when you look at your energy consumption and how it's being used and the time of year that it's being used, that you have a problem that you need to look into. The HVAC systems were consuming 50% more energy than required. That's because of the simultaneous heating and cooling, negative pressurization, the makeup air restrictions, the VFDs operating at higher than necessary static pressure. And the overall utility consumption was estimated at 40% more than it needed to be. The savings was over $100,000, which would have paid for another professor probably. We need to look at how we're using energy in the United States, as we previously talked about. Transportation, a lot of the car manufacturers are looking at ways to improve their energy efficiency of their vehicles. They're looking at the drag coefficients of the vehicles. They're looking at weight, which is what requires the amount of energy to move the car down the road on the freeways and highways. You have, from an industrial perspective, you have manufacturers that are improving the performance of their process. One of my clients is taking waste material to generate steam that is then used to drive a turbine that produces electricity, but also has energy to be used in the manufacturing process. These are all things that are happening in the world of energy to improve performance and reduce greenhouse gases. In buildings, we have a great opportunity to increase performance, utilizing commissioning in that process, as well as ongoing commissioning to measure the performance of those buildings over time to keep them performing in accordance with what the intended level of performance was from the design perspective, but also to impact or find out the deterioration as a result of equipment malfunction.
So having said why it is important that we reduce energy usage, let's talk about how we can actually do that. And of course, that's where the difficulty usually lies. It's one thing to have the intention to do something good. It's very different to actually be able to do it. So we're going to focus today on controls in particular. Obviously, commissioning extends across a number of other elements of a building, such as the actual installation and faulty hardware. But it seems that controls being the most unseen element in a building, meaning it's not obvious to the naked eye whether something is working or not when we're talking about controls. it's therefore much harder to correct when something is wrong. And we're going to start with the overall process of where the faults may lie, which is usually at the outset of where controls are created, namely in the engineer's mind. So it's the engineer's job typically in a building to write the control sequence. And then there are a number of steps, which we're going to talk about in a second, and how these are implemented. And every one of those steps can have potential errors introduced. But the most common error, I think, where some of these problems start is in the way the sequence of operation is written. And a common controls sequence will read something like, controls shall automatically reset set point to optimize energy use while maintaining comfort. That's not really a sequence that somebody can program. That leaves a great deal to the imagination. And that is the problem with many sequences where an engineer just doesn't have either the experience or the understanding in depth of how controls work in order to describe them in a way that a controls technician in the field can implement them. So there are a number of translation steps that have to occur in order for the sequence to be implemented and to work as intended. And the first step is usually that a controls technician translates the control sequence, which is in English, into some programming language. And at that point, there's usually also a disconnect because the engineer often cannot read the programming language, and the controls contractor may be misinterpreting what the engineer thought, or it may in fact be such a loosely worded statement, like the one I just read, that it's impossible to know exactly what the engineer meant. And the controls contractor, because of time pressures and other real world effects, may simply decide that he's going to pick some interpretation. And that leads to controls that don't perform the way that they should. Oftentimes when we look at buildings, controls don't even meet code. And unless somebody digs in and finds that out, the building simply gets handed over and then lives for the next 20, 30, 40 years with those faults built in without anyone noticing. So the problems are that the controls are badly understood by most project partners, including the owner, the general contractor, other people whose job it is to sort of vet what happened and accept it. The problem is also that controls, just by nature of the controls, by nature of the steps of construction, are usually at the very tail end of the construction process, and they're squeezed into a very tight schedule where it is difficult to do work effectively and to double check things because you're out of time. Then there's also the issue of cost. Of course, all controls contractors have to compete with each other, and ironically, the less checking you do, the quicker the job goes. So there's a sort of built-in incentive not to cross every T and dot every I. And on top of that, which is potentially somewhat counterintuitive when we're saying we want to reduce costs, the controls are in fact typically rewritten for every job. So rather than having a standard library of programming that somebody can choose from, the controls tend to be written specifically for every job, meaning the potential for introducing errors and relying solely on the years of experience that the controls contractor in the field has are also present on every job. And I think historically there may be sort of a full circle effect here, where initially controls weren't programmable. You know, pneumatic controllers didn't have much in the way of programming. And then the first set of controls that became quote unquote automatic or DDC or digital controls actually had canned sequences. Canned meaning they were just from a very small library, and all that the contractor implementing them in the field could do was to select option 1, 2, or 3, something along those lines. But it turned out that those were inflexible and didn't meet the needs of the much more complex buildings that we have these days, and also of changing codes. And so manufacturers went away from just the canned sequences in order to be able to deliver products that would meet code and would meet more complex designs. And that's why currently, we're back to a state where controls are basically made to measure, but with all the errors that we just discussed. So typically the result is, unless there are many capable eyes on the job and there's time to do it, the result is typically that the original design intent is not achieved, such that a building, even new, does not operate the way it was meant to, but certainly a couple of years later does not operate the way it was meant to. And that leads to poor temperature control, increased energy use, and a host of other potential issues that, unless reviewed and recognized, just stay in the building for years. So this has obviously been a well-recognized issue in the industry for a long time, but complex enough to where a simple solution wasn't apparent. So for a number of years now, ASHRAE has been working on producing a guideline that distills the best practices of controls design into a guideline that can then be copied, such that the first step that we talked about a minute ago, which is that the engineer has to rely, when writing a control sequence, on their personal experience and knowledge, that step is now taken out of the equation because they can rely on the combined knowledge of the various engineers who have worked with ASHRAE to develop Guideline 36, and basically take the best of all the engineers' experiences and use that for their job. So the Guideline 36 is currently published in its 2018 edition, but addenda are constantly being added, and the scope of the equipment that's currently in Guideline 36 for best in class practice is limited to air handlers and VAV terminals at the moment. But it is going to be updated continuously for years to come, such that at some point, more extensive or elaborate sequences for chiller plants and other equipment like all electric plants, chill beams, what have you, will be added. So there's a added benefit, not just for the engineers who can now point to a sequence in Guideline 36 when they write the sequences for their particular project and know that those sequences will actually be energy efficient. Sort of relieves them of some of the responsibility of making sure that they actually have good sequences, but also lets them point to well-crafted language that a controls contractor can understand that isn't open to interpretation. But much more to the point, ASHRAE has also undertaken the additional effort of involving all the controls contractors to allow them to write these Guideline 36 compliant sequences without being specific to a particular job. So they can create a library, and that can then be used in the field by field technicians in the same way that an engineer uses them, namely by pointing to an element in that library and without having to reinvent the wheel, simply using it. So if applied correctly, not only does it take some of the errors out and at the engineering stage, it also takes them out of the equation in the implementation stage, where the controls contractor can use, once again, as in historical days, a pre-canned sequence. So the only thing that's required to make that happen is for all the various controls contractors to actually program Guideline 36 sequences and have them in their library. There isn't an immediate financial benefit to the controls manufacturers in that regard, but there certainly is an immediate benefit to every one of their vendors, to every one of their dealers who implements sequences on a daily basis, because obviously it is much easier to use predetermined sequences than to write them specifically for each job. So that should lower costs ultimately for everyone involved, and it should take out two of the major error factors that occur during normal construction, which is the writing of the sequence and their interpretation. And of course, it also will hopefully eliminate some of the problems that we're currently seeing, because this is pushed at the very end of construction when there is no time. Because if you don't have to think about the sequences as much and you don't have to debug them because they're specific to the job, that saves time. So hopefully there's then more time left to actually do the testing and verify that everything is hooked up correctly. So those are the steps that, if this is applied correctly, will have a major benefit. And of course, for commissioning, there are also, and we're going to talk about that a little bit in the last segment here, there are more automatic tools that come on the market as we speak. And those tools can then also use Guideline 36 as what they are comparing against. The fault detection mechanisms can check against known behavior, because if you're Guideline 36 compliant, you can automatically test whether a sequence does something in an automated commissioning tool, for example, and figure out, without having to program into that tool, the specific sequence for the job, because you can refer again to Guideline 36. So let's look at some of the examples of how this works when implemented. So we're going to look at 2 case studies here where Guideline 36 was applied recently. One of these was an office building. This was in Redwood City in California, 140,000 square foot, fairly recently built office building, 1999 construction. That's about 20 years old, 5-story building, which already had digital controls. And the retrofit here was aimed solely at replacing the existing sequences with Guideline 36 compliant sequences, and the repairs of a few components such as actuators, which had failed over the 20 years. And the result of that was a 15% savings for whole building electricity. That means essentially a software change only, largely. I mean, yes, there were a couple of broken actuators, but the main elements of the retrofit were a controls change, saved 15% of the entire building's energy footprint. And in addition, it saved 56% of the natural gas usage in the building. So heating consumption or natural gas consumption dropped by more than half, which ultimately, in terms of looking at the controls implementation cost, resulted in a 7-year payback for the owner. But like we said earlier, the drop in gas usage obviously has effects on taxpayers in the larger sense as well. The second case study was a medical office building, also in California. This is a 200,000 square foot facility, 2-story, again, built in 1990. So this one was somewhat older. This one was about 30 years old, and still had pneumatic controls for the zone terminals. So in this case, the air handling units were replaced, sort of an end-of-life replacement. The AV terminals were replaced with digitally controlled ones, and all the control sequences changed to Guideline 36 sequences. And as a result, the overall building energy reduction was 38%. So again, it's not just the HVAC portion which got a reduction and a much smaller reduction in the overall energy footprint. The overall energy footprint was very noticeable at 38%. And the chilled water reduction was something similar. It was 38% as well. And the natural gas, or in this case, the hot water energy savings, once again, were more than half of the pre-construction consumption. So this points to the fact that the effects of reducing reheat are substantial. And the effects of using demand-based control sequences, which are at the heart of Guideline 36, have very significant effects on energy use. And what the demand-based sequences simply mean is all the parts of the system communicate with each other, and only when air or heating is needed is it actually supplied. And this goes hand in hand with things like occupancy sensing, for example. Jay was just mentioning that, schedule changes occurred because a professor wanted to go into a building at night, and as a result, because it was the easiest thing to do, the schedule was changed to 24/7. Well, when Guideline 36 sequences are applied, the same use case could apply without any intervention, because the system would simply know by virtue of occupancy sensors being triggered, even if it is in the middle of the night, and be able to serve just those zones and run everything else at very low volumes. And do the same thing as well for buildings just on a daily basis, where if somebody goes to lunch or half the building is unoccupied, as is often the case, then those parts of the system don't get served. So having demand-driven resets for everything from the air handling units or a chiller plant down to VAV terminals and reducing reheat are the main elements that make Guideline 36 more effective. There's also a lot of additional alarming and troubleshooting, such that when things go out of calibration, as they always will, that there are alerts to the operators to make that visible. So as we just said, Guideline 36 at the moment encompasses in its 2018 edition just air handling units and VAV terminals, but there is a list of addenda that is continually growing that adds additional equipment. And then in future editions of the guideline, the plan certainly to tackle pretty much all the major pieces of equipment that exist in mechanical systems.
Owners face a number of challenges, and even knowing that their building is not performing. Well, we have building automation systems in a good majority of buildings in the United States. Most of those systems are not being used to their fullest capacity. Part of the reason is that they're legacy systems. They don't have the memory. The technology doesn't allow the addition of additional memory, so it requires some expense to go and modify those. But having the information is power, and it really can help the owner as well as the O&M departments understand what's going on in their buildings and focus in on eliminating occupant complaints as well as reducing energy consumption without just overriding the controls that are, as Reinhard pointed out, a quick fix that often disguises the real problem and ends up increasing energy consumption and carbon emissions. Ongoing commissioning is a process that can help existing buildings owners to continuously improve and maintain high-performing buildings. Through monitoring and analysis of building performance, using ongoing commissioning, looking at utility usage and consumption, looking at how operations and maintenance is expending their resources, what their activities are, understanding occupant productivity and how their comfort is associated with that, and how to optimize that is all very beneficial. Giving the owner the tools to effectively manage their assets is really about adding money to the bottom line. As I said, information is power, and it provides visualization to understand complex problems that are allowing effective solutions. As you can see here, we have a blue and orange portion of the graph. It shows the average of about 3 to 4 kilowatt hours per floor. This is a two-floor or two-story office building, 33,000 square feet, recently renovated. They were able to put in the sensors to be able to obtain information on their energy use. And you can see here, when you add just the plug loads, which is what the blue and orange line represent, they're consuming 6.5 kilowatt hours on average per hour from 9 p.m. to 7 a.m. So that's 10 hours, 65 kWh per day, 23,000, almost 24,000 kWh per year, which is a result of 22 kilotons of carbon emissions from just this small 3,000 square foot office building. This is a VRF system. It's in an open floor plan. What you can see is that we have simultaneous heating and cooling occurring, which is very comfortable for the occupants, but is twice the energy consumption than it needs to be. Now with VRF systems, you've got a very close control of temperature as far as when you go from heating to cooling. In open floor plans, you can have crossover of controls where you see this kind of fighting, where you see one in heating and one in cooling, because you haven't calibrated the sensors for both zones to be accurate, or you haven't changed the control operation to be able to utilize an averaging of the two to be able to control them so they're not fighting each other. It's really important, you know, and that's part of what commissioning does, is when you go in there and take a look at this and monitor what's going on and how the systems are operating, you can identify opportunities to improve performance as well as occupant comfort in the building. Here's a dedicated outside air unit. It's got 5 separate stages of DX cooling in it with non-interlaced coils and dampers. What you see in the spikes is the operation of each one of the systems, each one of the 5 cycles ramping from up and down, because there's stratification in the unit. This kind of information, you know, you think because you get a piece of equipment from a name manufacturer that's supposed to work right. Often we find problems in how those pieces of equipment are performing, and they're not really performing as the manufacturer's design intended, as in this example here. You have the system fighting each other because of internal conditions and how that system was designed, or that piece of equipment was designed. That can be corrected if you know that you have the problem. That's where the information of monitoring has so much power. So LB&L has done a number of studies on commissioning as well as monitoring-based commissioning and existing building commissioning. As you can see here, they have found significant energy savings from being able to have the buildings commissioned. Now, this is a smaller study they have, and is included in the references that we've included in a couple of the slides, where they have studies that have included 1,500 buildings across the United States. We have a great opportunity to improve the performance of the existing building stock of commercial buildings in the United States. And we need to be able to implement that to be able to reduce our impact on energy consumption as well as climate change. Certainly this is a high-tech laboratory facility. It has been working on all of the research necessary to go to Mars, which we recently achieved. Not all of it, but a number of aspects of it. Built in 1957. It's a large facility, 300,000 square feet. They had a lot of labs as well as offices in the building. We went back after we finished the existing building commissioning process for the facility, and we had monitored the results of what we had modified over the previous period for 1 year after we completed the existing building process. And see, these are results of what came from that existing building process is a 26% reduction in work orders for that specific building, saving $40,000 a year. Changes in how occupants perceive their facility from a thermal comfort perspective. Reductions in heating and cooling cold calls, as well as having improved occupant performance because of a higher comfort level. You know, when somebody's uncomfortable, they do a lot of things. I have many pictures of unit heaters in offices where people have been uncomfortable, or they put in fans. All of that adds to plug load and is often not controlled besides the individual control whether the building is occupied or unoccupied. There is certainly you need to make sure that you don't have to have those supplementary devices that you have looked at why the occupants are unhappy and be able to address that. And occupant surveys are an excellent opportunity to understand how people perceive their spaces.
So what this case study shows is that it isn't, in fact, even just energy use that we're talking about, but the reduced work orders and increased occupant satisfaction have multiple benefits to the owner and or tenant as well. So there are lowered operating costs, not just in the utility bill, and that is often something that's not directly included when we do simple payback calculations. In addition, the higher workplace satisfaction and the increased tenant productivity is also something that is usually not put into any financial calculations because it's so hard to quantify. There's been a lot of research done on that, but it seems obvious that happier occupants do better work, but there's no direct financial result connected to that typically. But it is one of the real effects of having better performance for the building. And then, of course, based on better occupant satisfaction, it also raises potentially the leasing value to a landlord because, of course, a building that is known to be uncomfortable is not going to fetch the same rents as a building where tenants are really happy. So there are side effects that aren't often captured explicitly in payback calculations, but that are nevertheless real for a well-run building.
There are platforms out there that can help, and we'll discuss more of this a little bit later in the hour. But there are platforms out there that you can put in place that take the information from the building automation system, analyze it, prioritize, and identify when problems are occurring in buildings. They usually prioritize based upon what it's costing you. And we have an example of that later on besides this. But it allows you to go in and also analyze to find what the root cause is, because these systems, as you can see here, is a typical page out of one that identifies what the level of energy consumption is, the impact on operations and comfort aspects of how the building is being operated, and can tell you where you have a potential problem and give you ideas about what to be looking for. But they don't solve the problem for you. That requires a little more detailed analysis of the problem, which they have tools to do that, to be able to be more efficient about when you're going to assign personnel to go out in a truck and actually address some of these issues. And this is really a key tool that a lot of different organizations, especially if they have a lot of buildings, are using to effectively manage their O&M costs and identify the areas of opportunities as well as efficiency of assigning personnel. If I could get the Excel spreadsheet to move up and down in a PowerPoint presentation, what you would see here, this is an office building. There's 2 towers of this office building in adjacency. This is showing where you have non-heating occurring, heating occurring, as well as cooling. This is a office building, again, in Atlanta, Georgia. It is July 19th. It's 77 degrees outside. And what you see is the perimeter zones are in heating. If you would look at, if I was able to show you this timestamp on an hourly basis, how this changes, you would have seen these spaces going from cooling to heating, back to cooling, back to heating. You know, design engineers are given specific criteria about occupancy, you know, what's expected, and they design for the maximum loads. When you're monitoring and you're doing an analysis of systems, this gives you an opportunity to adjust how that system is operating, so you're not having the systems going back and forth between heating and cooling when you don't really have a people population yet. And Reinhardt talked about it a little bit earlier about having occupancy centers. A lot of the zones, not particularly in this building, but in newer designs, are utilizing occupancy sensors in the space to turn on lighting to also designate when the space is occupied and making it operate at occupied conditions. So again, this is where having information is power. That information gives you a continuous feedback that you can go to the CEO and the CFO, you know, which O&M staff that has a typical problem, they may understand that they have a problem. They don't have the information that they can actually take to a financial officer and be able to tell him why it's a benefit to spend X dollars to improve performance and reduce utility costs, as well as improve occupant satisfaction and productivity. Ongoing commissioning has the ability to do that kind of analysis and provide it to the owner, as well as you can do this in existing buildings when you're doing existing building commissioning, to give that more specific information so that you can make good financial decisions or good decisions on how you want to use your financial and human resources. It also can be helpful to communicate what the issue is to the technician, and you can have technicians that are focused in on specifically problems that you're sending the right person out there to solve the problem, which reduces the back and forth if you don't get the right guy on the job. Because not all technicians are suited for all problems in buildings. So this is another case study. It has to do with a university in Mississippi. It is about collection of information and being able to use it for management. In this case, we were monitoring 39,000 points, almost 40,000 points, covering 70 buildings at 15-minute intervals. And we analyzed over 3 million, almost 4 million pieces of data a day. The review of over 1,000 BAV boxes identified 30 that were responsible for consuming over $22,000 a month in additional electrical consumption. This is where monitoring-based commissioning, ongoing commissioning can be very cost-effective. It can help with facility persistent performance. It can improve occupant satisfaction and productivity, and you have more efficient use of operational staff. It also has a positive impact on the environment and financial impact to the bottom line and lowering the total cost of ownership. Ongoing commissioning as well as monitoring-based commissioning have limits. You really need to understand what changes are being made and the requirements of that building. you look at thermal capacitance of the building when making decisions. You look at operational hours. You look at all of those kinds of things, and your ability to assess that information is what the limiting factor is. And you know, a lot of the smaller buildings out there typically do not have building automation systems, while the larger ones that we pointed out earlier do. They still require a lot of analyzing, collection of data, and that's very time consuming, and having platforms can help you improve that. More technology allows better assessment. You have operational staff, having their difficulty of conveying the problems to ownership without having that information either provided by a platform or provided by a commissioning provider who's there. Even if you have one of the platforms, you need to have skilled technicians, engineers, commissioning providers that are able to understand the information that's coming in and be able to give good direction to what needs to be done so that you can operate more efficiently from a O&M perspective as well as an energy efficiency perspective.
So moving on to the last portion of our presentation here, which is how do we use new technologies to make our commissioning efforts more efficient and more effective? So Jay has just presented obviously some examples of where knowledge is power. And so we're going to talk a little bit about that portion of things in how more data can be leveraged. We're going to talk about a few other items not directly related to controls. But starting off with controls, there is an obvious need, in order to have eyes and ears on the job, there's an obvious need to collect data. And now most buildings these days, certainly most new buildings, also a number of existing buildings, have building automation control systems in there. The point I think that we want to make is that their interfaces typically don't lend themselves to the type of data collection we were just talking about. So when an operator for a building uses the building control system interface, I think it's a little bit like someone driving a car. There's a dashboard, and that's sufficient for you to operate the car. But if there's a problem, you would typically take it to the shop, and they would put in the diagnostic plug, under the dashboard, and use a computer to get a better readout of what's happening inside the engine. So that's the kind of data that we would need to actually assess whether a building works correctly. And in most cases, the building automation system front end, or equivalent of the dashboard in the car, isn't good enough to do that. So there are many flavors of where the data that's collected can be stored in a cloud and then can be accessed by third-party software, or like Jay was just mentioning, there's also third-party software that provides a dashboard of its own, specifically aimed not at daily operation, but at finding out problems. So those are tools that should be considered, because it is typically a fallacy to think that just because you have a building automation system, the operator would now be able to do the kind of troubleshooting that we're talking about here for building improvement. So next to those advances in cloud-based data management, there are also changes in the available equipment that we have as engineers to choose from. And that goes for both existing buildings and new buildings, because of course you can replace existing inefficient gas boilers with electric heat pumps these days. And the rise of all electric plants is something that will force a lot of engineers to rethink the way they've been doing things. But it does bear thinking about whether you're actually making an improvement by doing that. And the question of whether you're improving the overall energy efficiency, or in this case, carbon footprint of a building, is related to the utility grid that you're on, which varies by state. So if you have a building in a state whose electricity grid is mainly powered by burning coal, for example, well, then changing to an all-electric system isn't going to do much good. So there's an easy way to find out in mostly a real-time basis what the sources are for a particular grid. And so, for example, in California, which again is where I live, so it's close to my heart, but there's a graph that's shown here with the link of where to collect this data. There's a graph that shows that the carbon emissions have roughly dropped by half in the last 6 years. So even though our energy use has not gone down, the type of energy provided is now, if you will, twice as clean because the carbon footprint is half as much. And that's largely because of a switch within the utility sector to more renewable energy. Now, that isn't true for every state. And the Energy Information Agency has a dashboard, which is in beta at the moment, but allows you to see the energy mix of all states. So you can go there and take a look at what portion of your utility grid is sourced by coal, natural gas, petroleum, renewable energy, and so on and so forth. And that should be part of the decision-making process to say, does an all-electric plant make sense? So for example, in California, it already does. Not necessarily the case in every state. Something worth checking before deciding to make a switch in that direction. So looking at some of the technologies for making building walkthroughs possible, we have 3 examples here on the slides that are coming up. And when you download the slide deck as part of the materials that you get, you'll see a little video button on the slide. When you hit that, you can watch a video of what I'm going to talk about here in these 3 different cases. So the first one is an example for a job in San Jose, and it was used to talk about, in this case, access to some VAV terminals. When we first walked the job, it was already clear that the spaces were very high, and there was a question and concern about how those would be accessed. And so documenting the progress of construction and making the point that, you know, the ceiling would have to have an access door there and potentially be walkable so that somebody could stand on top of the ceiling to get to the actuators was the kind of discussion topic that's hard to illustrate in a construction meeting where everybody's sitting around the table without some of these tools. But with those tools, it becomes readily apparent. So when you look at the video of that, you'll see the same location in different points over time as it gets built out. And you'll also see the ability to tag terminals in the video, in the 3D model that's built there, to tag them such that when you discuss those locations with somebody else, something like you actuate hard to access or comments of that nature pop up in the photo. So regardless of who's viewing it, you can leave breadcrumbs, I guess, for discussion or for attention within the location that is completely understandable to somebody looking at this. So the next slide shows a similar system. All the manufacturers of those systems have been removed because it's an ASHRAE presentation, but just to show there's multiple different platforms that can do similar things. That platform shows a approach where the 3D model is actually used to do the notation of punch list items, of issues log items, and things of that nature, not in a list or not just in a list as it is usually done, but within the model, so that as you look at something that you want to resolve, the issues log tag or the fix-it punch list tag is mounted right to that piece of equipment. So it also becomes much more intuitive when somebody says this lever needs to be moved or something of that nature. Well, if you're standing in front of it, seeing it, it becomes immediately obvious what the comment means. And therefore it is much more efficient in resolving complex problems that are related to space. The last example here is from The Berkeley Laboratory, LBL, the Lawrence Berkeley Laboratory, which has a public website. And so they've posted the geometry of their advanced light source, the ALS building. And that's undergoing a major retrofit at the moment. And as part of that major retrofit, to allow for space coordination and to allow for cross-checking of dimensions, they've put that in a system that, again, is accessible online. And so the link for that is in there. Now, that particular system allows not just the creation of a virtual model that you can walk through, but in that model, you can also snap dimensions. So as you walk through and you want to know, for example, what is the distance between the front of a control panel and the wall, things of that nature, you can actually measure up within the model and take measurements that you didn't originally know that you wanted. So that's another platform. So there are multiple ways of leveraging time spent in the field across multiple professionals who can then use that data without having to themselves walk in the field. So lastly, I'm going to talk about one free tool here for most of the controls, eyes and ears that we were talking about earlier, the methods that we have for making data visible or visually interpreting it such action can be taken, are commercial and often affordable, but we're also going to highlight very quickly here a tool that is entirely free for those working on buildings without an energy information system, for example. And that is the Universal Translator. And there's a link in the slide deck. So that's a tool that was developed by PG&E, one of the utilities here in Northern California. And it is free for use by engineers, commissioning providers, and allows the use of visualization of data. It has a whole bunch of built-in automatic routines as well for checking economizer operation and things of that nature. And that tool can be used free of charge. And there's also multiple training sessions a year that PG&E gives, which can be attended virtually. So whether or not you're in California doesn't really make a difference. You can download the tool and get trained on it remotely. So one element of implementing energy information systems and fault detection is that they're not part of the normal building automation system. And so I think the realization is growing within typically larger campus style systems that building automation system alone isn't enough. But it is worth talking about if you're either a commissioning provider or an engineer working on a job, to talk to the owner and make the case that some of these systems may actually be cost effective, even if they're not normally on somebody's radar and appear to be, a add-on that the owner would not have considered otherwise, and point to some of the benefits that we've outlined here, such as reduced maintenance cost, better occupant satisfaction, that can really only occur when continuous checking of the building's operation takes place. And like we said, that is typically not the case through the normal building automation system.
Having the platforms in place without somebody who's actually utilizing them is a waste of money. It's really important to have someone who is correlating that data, because there is a disconnect between some of the systems. Depending on what platform you're selected, you may only have the fault detection portion of it. You may not have the energy information systems brought up, or you may just have one or the other. It's really a combination of the three elements of having the technology and having somebody who's going to pay attention to the technology and actually provide value, whether it be internal or external to the organization. ASHRAE has a number of wonderful resources for you to go to. Reinhardt talked about Guideline 36, which is certainly about standardizing controls. But we also have the commissioning standards. They're all under SSPC 300. We have standard 202, which is the commissioning process for new buildings. We have standard 230, which is in the process of being completed. That is for existing buildings. We also have guidelines that help you with best practices, 0 and 0.2, as well as we are defining the ones for the individual HVAC, smoke control, systems manual, etc. I really want to thank Reinhardt for his contribution to this presentation, and thank you to ASHRAE for allowing us to have this time with you, and thank you for coming, and thank you for your time.